The Big Bang is a concept that has framed how we could decipher the universe, outlining the foundation of modern cosmology. According to Einstein's hypothesis, also referred to as general relativity, the Big Bang marked the moment the universe began its expansion, indicating the origin of all matter, energy, and space. This event occurred roughly 13.8 billion years ago and initiated the vast universe we observe today. However, recent advancements in cosmology suggest that the Big Bang most likely wasn't the absolute beginning. Instead, there could have been a phase before the explosion that was equally crucial in shaping the universe as far as we understand. This earlier period is known as inflation. Inflation is quite possibly one of the most exciting aspects of modern cosmology. It proposes that before the hot, dense phase of the Big Bang, the universe went through an incredibly brief but dramatic expansion. During this phase, the universe was duplicating in size at a shocking rate. To put this into perspective, if the universe began smaller than an atom, it could have expanded to become incomprehensibly larger than the entire observable universe in just a minuscule fraction of a second, around 1/4,000,000th of a second. This inflationary phase did not last long. However, it played a crucial role in forming the universe. When inflation ended, the energy driving the expansion was released into space, warming it and producing the particles of matter that make up everything we observe in the universe. In many ways, inflation is the precursor to what we consider the Big Bang. While the theory of inflation is widely accepted in modern cosmology, several unanswered questions remain. For instance, we still do not understand what started inflation, what made it stop, or how long it lasted. These remain open questions in cosmology, and answering them is vital for a deeper understanding of the universe's origins. Before inflation, the universe existed in an incredibly dense, tiny region of matter, often called a singularity. From this singularity, inflation began and eventually led to the formation of atoms, particles, stars, and galaxies. The idea of the Big Bang as the origin of everything is compelling, but modern cosmology paints a more complex picture. Some theories suggest that the universe underwent a phase before the Big Bang. During this phase, inflation made the universe grow at an extraordinary rate, expanding in size by a factor of approximately 1,000,000,000,000 in a fraction of a second. This brief expansion was fueled by a strange form of energy that permeated empty space. When inflation ended, the energy that had driven this expansion was converted into particles, warming the universe and triggering the hot, dense state we refer to as the Big Bang. This inflationary phase was cold and empty, but set the stage for the production of matter and the universe we observe today. One of the more theoretical ideas in modern cosmology is the concept of eternal inflation. This theory proposes that inflation didn't stop all at once. Instead, it ended in patches, creating a vast number of bubbles, each potentially forming its own universe. Our universe would be just one of these bubbles. According to eternal inflation, there may be an infinite number of such universes, each with its own set of physical laws and constants. This is where the concept of the multiverse becomes an essential idea, the notion that our universe might be one of many, or even an infinite number, of universes. If this idea turns out to be true, it could explain why our universe appears so finely tuned for life. In this multiverse scenario, every possible combination of physical laws might exist in different universes, and we happen to live in one, where conditions are just right for stars, carbon, oxygen, and other elements necessary for life to exist. While ideas like eternal inflation and the multiverse remain speculative, the concept of inflation itself is grounded in observational evidence. The most substantial support for inflation comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. This light contains valuable information about the universe's earliest days, helping researchers understand what happened soon after the Big Bang and providing support for the inflationary model. One of the most significant discoveries came from the European Space Agency's Planck satellite, which captured highly detailed images of the CMB. These images reveal subtle variations in the temperature of the early universe, variations that match predictions made by inflationary theory. This experimental evidence strengthens the view that inflation is not just a theoretical concept, but a key part of how we understand the universe's origins. Understanding the Big Bang and what came before it requires unifying the two main frameworks of modern physics, Einstein's theory of general relativity and quantum theory. General relativity describes the large-scale structure of the universe, including the behavior of galaxies, stars, and planets. Quantum theory, on the other hand, explains the behavior of particles at the smallest scales. To answer fundamental questions in cosmology, such as what the universe is made of and where it came from, researchers must develop a theory that unifies these two frameworks. Such a theory would allow us to understand not only the Big Bang, but also all the conditions that led to it. One of the most astonishing aspects of the universe is its size. The most distant objects we can observe are about 47 billion light-years away, meaning the observable universe is about 94 billion light-years across. This might seem odd, given that the universe is only 13.8 billion years old. How can the universe be larger than the distance light could have traveled in its lifetime? The answer lies in the fact that the universe has been expanding over time. As the universe expands, the space between objects increases, making distant objects farther away than light could have traveled in that time. Most researchers believe the universe extends far beyond the observable part. In fact, it is plausible that the entire universe is infinite in size. The observable universe is essentially the part we can see, limited by how long light has had to travel since the Big Bang. There may be vast regions of the universe we will never be able to see. Even if the universe is infinite, the question remains: is there anything beyond the universe? Most scientists are cautious about this idea. If the universe is infinite, then by definition, there is no outside to it. The universe would simply continue endlessly. Even if the universe is finite, it might not make sense to talk about anything beyond it. Beyond implies something outside space itself, but space is a property of the universe. So the idea of something beyond the universe likely doesn't apply in any conventional sense. Have any physical meaning. Further, because the beginning of the universe is a subject of great attention and wonder, so too is its inevitable end. The prevailing contemporary theory is that the universe will continue expanding indefinitely. This is attributed to a phenomenon called dark energy, which is causing the universe's expansion to accelerate rapidly. Before the discovery of dark energy, researchers believed that the universe's expansion would eventually slow down due to the gravitational pull of matter. There was even a possibility that the universe could stop expanding and begin contracting, leading to a big crunch. However, dark energy appears to be pushing the universe apart at an ever-increasing rate. If this acceleration continues, the universe will keep expanding forever, eventually reaching a state in which galaxies drift so far apart that they become isolated from each other. In this scenario, the universe would become cold, dark, and depleted. Stars would burn out, planets would drift away, and matter would eventually decay. This is referred to as the Big Freeze, or heat death, of the universe. The narrative of the universe, from the Big Bang to its possible end, is one of the most important and complex stories in science. While we have learned an incredible amount about the origins of the universe through the theory of expansion and the study of the cosmic microwave background, many questions remain unanswered. What caused expansion to begin, and what will cause it to end? What lies beyond the observable universe? Is there a multiverse? And if so, how many other universes might exist, As researchers continue to explore the universe using advanced technology and theories that merge quantum mechanics with general relativity, we will undoubtedly gain deeper insights into these mysteries. The journey to understand the universe is ongoing, and every discovery brings us one step closer to answering the fundamental questions of our existence. The study of the universe's origin and structure is not merely a scientific endeavor. It also raises profound philosophical questions about existence, reality, and our place in the cosmos. One significant area of interest in cosmology is the nature of dark matter, which is believed to account for approximately 27% of the universe's mass energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is essential to making sense of the formation and behavior of galaxies and larger cosmic structures. Ongoing research and observations have offered insights into dark matter's properties, but its exact nature remains elusive. Some candidates have been proposed, including WIMPs, weakly interacting massive particles, axions, and other exotic particles. However, as of now, no direct evidence of dark matter particles has been found. The search continues through a combination of terrestrial experiments, astrophysical observations, and simulations that model how dark matter shapes the large-scale structure of the universe. Another key area of exploration is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy is estimated to make up about 68% of the universe's total mass energy content. Its discovery was unexpected and has led to numerous hypotheses, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is critical, as it will determine the ultimate fate of the universe. Scientists are studying its influence on cosmic structures and seeking to determine whether it remains constant over time or evolves. In addition to dark matter and dark energy, the study of large-scale structure formation provides major insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, have revealed how matter clumps together under gravity, forming the complex structures we observe today. Simulations run on supercomputers help scientists understand how these structures developed over billions of years and continue to evolve. Astrobiology also intersects with cosmology, as researchers seek to understand the conditions necessary for life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has intensified, with thousands discovered in recent years. Some of these exoplanets are located in their stars' habitable zones, where conditions may be suitable for liquid water to exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and the factors that make a planet hospitable. Finally, the role of fundamental physics in cosmology cannot be overstated. The quest for a unified theory that combines general relativity with quantum mechanics continues to challenge physicists. Theories such as string theory and loop quantum gravity aim to bridge these two frameworks, offering explanations for phenomena like black holes and the early moments of the universe. As technology advances, so does our ability to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are revolutionizing our understanding of the universe by providing unprecedented detail of distant galaxies and cosmic events. With each groundbreaking discovery, we move closer to unraveling the mysteries of the universe's structure, evolution, and ultimate fate. The study of the cosmos is a rich tapestry of scientific inquiry and philosophical reflection. From the fundamental forces shaping vast structures to the search for extraterrestrial life, our exploration reflects humanity's enduring curiosity about the universe and our place within it.